Okay. So let's solve a few of the questions in this session. So let's start with this question. So what this question is saying, let A be this matrix and B be a column. Okay. So A be this matrix and B be some column. For which of the values of K does this AX equal to B have a unique solution? So they want to have unique solution, right? So let's just do one thing. Let's first, just have this augmented way to write this matrix, which means 1, -1, and K, and then 0, 1, and 2. And then if you augment it, you will be getting 1, 0, 1, right? Now, can you do the elementary row operations to find out the value of K? So let me just do the elementary row operations. So for example, if you just augment it and then if you do elementary row operations, you will be getting this as one of your metrics, okay? This as your reduced matrix. So you are getting this after elementary row operations, right? So here, one is the pivot, this is the first pivot, and then this one is the second pivot, right? So this is the pivot, this is the pivot. Now, if you want to have unique solution, then what you want to do? Unique solution. See, first of all, for the system to be consistent, okay, by the way, these two are linearly independent, right? I mean, these two are having the pivot, so these two are linearly independent. Now, for the system to be consistent, what do you want? You want zero non-zero situation, do you want? No, right? So basically, if this is zero, then this has to be zero. So for the system to be consistent. So you can say for consistent systems, for consistent system, you can say the zero non-zero should not appear, right? Should not appear. Should not appear. So which means if this is zero, right, then this has to be zero only. So whatever this is, which is actually -1 minus k, it has to be zero only. So which means k should be -1. Okay. So this way the system will be consistent. Okay. And automatically it will be just having the unique solution. The reason is that because these are all already linearly independent. So it will definitely be having the unique solution. So what is the answer here? Yes. So the answer is k should be -1. Okay. It is easy question. Let me know if there is any doubt in this question. Okay. So k should be -1. So C is the correct answer here. Yes. Now let's just move to the next question. So in this question, they are saying, let A be a matrix which is M cross N and B be the matrix which is M cross M. Which of the following statement is not true? Okay. For all such matrices. So they are saying is not true. Is BA defined? If you are having B which is N cross M and A which is M cross N, it is defined? Yes. Because M and N, this is common. So BA is defined, right? So that's true. But they are saying not true. So basically, you can say this is true. Actually, this is true. But they are asking not true. So let's just move to the next option. The columns of AB are linear combination of columns of B. See, is this true or false? The columns of AB. So which means if you multiply two matrices A and B. Okay. Now you get one matrix here, which is AB. Now columns of this AB are the linear combination of columns of A or columns of B. Can anyone tell me? This is important. Can you tell me? So here, these columns are linear combination of columns of A or columns of B. Just think about it. See, whenever you have AX, okay, whenever you have AX, suppose you have A into X. This is A, this is X. Now, don't you think this finally, whatever you are getting, this is basically a linear combination of columns of A, isn't it? So here you will be getting the linear combination of columns of A, right? But this is saying that linear combination of columns of B. So this is false actually. Okay. This is false. And they are asking what the false option. So as per this question, this is actually the answer. Okay. But let's just see other ways. AB is defined. Yes, if it is M cross N and N cross M, so yes, AB is defined. So this is true. The columns of AB and the columns of AB are linear combination of columns of A. Yes, this is true actually. Okay. So if they're asking the false option, then B is the false. Okay. B is the false option. Okay. So So answer is basically B. So here in one of the answer we have given example. Let's suppose A is this and B is this, then AB is this. So 1 2 is a multiple of basically is not a multiple of 1 1, right? I mean 1 2 is actually multiple of either this or this. Linear combination of this or this or this. Okay. Anyway, but I hope you understood. So here if you are having, see, if you are having two matrices, okay, A and B, and if you multiply these two matrices and finally let's suppose you get one matrix which is AB. Now these columns are basically linear combination of columns of A, right? Columns of A. Okay. Okay. We have been doing this since a long time, so now you know this, right? Okay. Now let's move to the next question. So this is the next question. What this question is saying: consider A and B, and there is a vector V. Which of the following is true? They are asking about the true option. So one matrix A is given, another matrix B is given, and then there is a vector V. So they are saying that V is a linear combination of columns of B, but not as of the columns of A. Okay. So they are asking whether this particular vector is a linear combination of columns of A or columns of B, like that they are asking. Okay. One thing you might notice here is that columns of B, okay, you can make this 0. So basically this is like, 2 into R2, R3, you can replace this R3 by 2 into R2 minus R3, something like this. So basically it will be 0. So basically you can see this is a pivot, and once you replace this will be a pivot. So basically these three are linearly independent columns. Okay, that's very easy to check. Let me just quickly tell you how to check it. So see, this is 1 0 0. Okay, I'm writing matrix B. Okay, this is 0 1 minus 1. This is 0 2 0. Okay, so if you just replace, this is anyway pivot. Okay, now if you just replace this R3 by R3 minus 2R2, then what you will be getting? Let me just write it. Okay, 1 0 0 0 1 minus 1, and then if you replace this R3 minus 2 R2, so basically anyway this is 0, so this will be 0, R3 minus 2 R2, right? Now 0 minus 2 into this, so basically it will be 2 only, right? So you will be getting something like this. Is this okay to everyone? That's very easy to check, right? So basically these three are pivot. Now what is the significance of this? You can say that since these three pivot, so they will be basically in R3, and three pivot, three linearly independent columns you have. So they are filling the space, okay? Filling R3. So is this a linear combination of these columns? Yes, actually any vector is a linear combination of these three columns, right? Because they are filling R3. So actually this vector is a linear combination of columns of B. That is for sure. But is this a linear combination of columns of A? That is what we need to know, okay? Or that is what we need to check. So, so basically you can say that if you want to get 1 and 1 here, okay, using this, so you have to basically multiply 1 here. I mean, these are just like identity vectors, okay? I mean, not exactly, but if you just look at the upper part, then you will say that, okay, you need to sum this, okay? So if you sum this up, it will be 1 1 2, not 1 1 1. So basically this particular vector is not a linear combination of this, but yes, this particular vector is a linear combination of columns of this. Is this fine to everyone? So what is the correct answer here now? The answer will be V is a linear combination of columns of B, but not the columns of A. So answer will be A, right? So answer will be. Is this fine to everyone? And what is the other way to do it? So basically you can check whether AX equal to B or BX equal to B has a solution or not. Okay. I mean, this is one other way to check whether V is a linear combination of columns of A or not. Okay. So using this also you can check. Great. So now let's just see this next question. By the way, is there any doubt in this question? Let me know. Or everything is fine. So how we checked it? How we checked it? We basically observe that, okay, columns of these columns are linearly independent. So anyway this will be linear combination of this, and then we checked it manually. Or other way to check it is basically is like this, that okay, AX equal to this V has solution or not, BX equal to B has solution or not. Okay, so this is the other way to check it, right? Okay. So now let's just see this question. So by the way, answer of this question was A, right? Answer of this question was A. Okay. Now let's just see this question. So let me know if everything is fine or there is any doubt till this point. Okay. Now let's see this question. In this question, they are saying that A be a 2 cross 3 matrix and V is a vector in R2. Okay. So 2 cross 3 means 2 rows and 3 columns. 2 rows and 3 columns, right? Like this. Now they are saying that A be the matrix which is 2 cross 3, 2 rows and 3 columns, and V be a vector in R3. This in R2 basically. It means two dots, right? Now consider the following two statements. The first statement is that A has at most two pivots. So yes, that is true. I mean, it cannot have more than two, right? Like where is the space for more than two? So yes, that is actually true. Okay. What about option B? Ax equal to B has a solution. Assuming Ax equal to B is a solution, then it has infinitely many solutions. Yes, if it is having solution, then since these must be linearly dependent, right? I mean, you cannot have in R2, you cannot have three. So if this is having solution, then yes, infinitely many solutions. So yes, this is also true. So that is why D is correct answer. Okay. So is this fine to everyone? Because they must be linearly dependent. Now, if it is having solution, see, it is not necessary to have Ax equal to B as a solution, but if it is having solution, then there will be infinitely many solutions because this is linearly dependent. Okay. So I can repeat it. So see, if you are having, okay, if you are having, let's suppose some solution, okay, let's suppose this is Ax equal to B, okay, this is A, this is X, this is Ax equal to B. So if you are having some solution, in that case, I mean, let's suppose you are having some solution. If this is linearly independent, then unique solution. If this is linearly dependent, then infinitely many solutions. Okay. If you are having solution, understood? So if this is linearly independent, then unique solution. Okay, linearly independent, then unique solution. Linearly dependent, then infinite solution. Okay. Assuming solution exists basically. Okay. Understood? Okay. So the solution could be trivial solution or non-trivial solution. Okay. If they are saying solution, it is not like they're talking about non-trivial solution or anything. Solution means it actually covers trivial and non-trivial both. Okay. Could be trivial solution is also a solution. Okay. We will be considering that also a solution. So basically, answer here is D, right? So answer is D. Okay. Now let's just move to the next question. Yeah, this question was interesting question. This question I've taken from, by the way, MIT. I've taken this question from MIT. So this question is saying that suppose Ax equal to 0 has solution of this form. Okay. Suppose this is the solution of X equal to 0. And using some unknown elementary row transformation or row operations, we get some R. Okay. On A, we get this. Now, what are the values of this A, B, C, D? That's what they're asking. Right? Okay. That's interesting. So see here one thing, that whatever is the solution of Ax equal to 0, okay, if you reduce this A to R, then Rx equal to 0 will also be having the same solution or vice versa. Basically, the solutions of X equal to 0 and Rx equal to 0 are same. Do you all agree with me on this? So solutions of both are same. I mean, this is the process, right? I mean, you reduce that to R and then you get the solution. This is the process to get the solution. So solutions of both are actually same. Is this okay to everyone? Is this understood? Okay. Now, if this is the solution of X equal to 0, then this must be the solution of Rx equal to 0 also. Okay. I mean, for any value of S and T, so just put S equal to 1 and this as 0, just for the sake of getting one vector. So you will be getting 1, 1, 1 and 0, right? So let me go to the next page. So basically, you will be getting one x as 1, 1, 1 and 0, right? This is one of the solution. Okay, this is one of the solution. One of the solution of ax equal to 0, right? Hence solution of rx equal to 0 also, which means if you take this r, which is 1, 0, 0, 0, 1, 0, a c 0, b d 0, right? If you take this r and if you take this x, which is triple 1 and 0, then this must be 0. Okay, this must be 0. I mean, this equation must be satisfying. So basically, if you do that, you will be getting a vector basically, which is uh, these three, right? You need to just add these three, 1 plus c 0. Okay, this vector must be 0. So you will be getting two equations from here. Similarly, you will be getting, you will be getting values of a and c from here, and similarly, you will be getting values of c, b and d if you just take this. Okay, because you are saying 0. 0 means you don't need to take this particular column. You will be having the equations only in b and d. Okay, so basically that's very easy. A is -1 and c is also -1 from this. Okay, and then similarly you can find out the values of b and d. So see here, a and c are -1s, and then if you just put this particular vector as solution of rx equal to 0, then you will be getting values of b and d. Okay. So isn't it, this particular question was very good. So how you found this question? This question I've taken from MIT. So this was actually very good question. Okay, just testing on the basics that okay, you need it should be clickable in your mind that rx equal to 0 and ax equal to 0 has the same solution, same set of solutions, right? Okay. So I hope that is fine. Okay, now let's just see this question. This question was also, quite interesting question. So what they are saying, consider matrix A m cross n such that ax equal to some vector has no solution. So don't worry about the exact vector. Now they are saying that ax equal to, b, or ax equal to some vector has no solution. So basically you can say ax equal to b for some b. Okay, for some b has no solution, and ax equal to b for some other b. Okay, for some other b has exactly one solution. Okay, so basically these two are the statements which are written here. Is this fine to everyone? These two are the statements. Basically, this exact vector doesn't matter to me, but yes, they are trying to say that for some b you have solution, for some b you do not have solution. Yes, the vector dimension is 3. Okay, so basically you can say the vector is in R3. So let me just go to the next page. So the columns of A will be in the R3 only, right? Because the ultimate vector was in R3. So, but you don't know the number of columns, okay? You don't know the number of columns, which is fine. But yeah, columns of A is in R3. That is for sure. Now, see here, they are saying that you have exactly one solution. So, you tell me if you have exactly one solution for some B, it means these columns must be linearly independent. Whatever number of the columns here must be linearly independent. Do you all agree with me? If you have exactly one solution, if there is a unique solution, then whatever number of columns you have, it must be linearly independent. Now, can you have four columns? Can you have four columns? Tell me. Can the four columns in R3 be linearly independent? No, right? I mean, you cannot have four columns because they must be linearly independent because of this statement. Okay, this statement is saying they must be linearly independent. Can you have three columns? Actually, this statement is saying you cannot have three columns because if you have three columns, then you are filling the space, right? Then in that case, you should be having the solution for every b. But if they are saying you do not have the solution for some b, it means you cannot even have the three columns. See, You cannot have four columns because you need linearly independent, right? Because the second statement is saying you must be having linearly independent columns. So you cannot have four columns, five columns, six columns. That is for sure. But you cannot even have three columns. Okay, that is what first statement is saying. The first statement is saying that no solution for sum B. It means three linearly independent you don't have. Okay, so if you have linearly independent, then there can be one or two. So basically, if I just ask you, how does the matrix look like? Okay, so what is your guess? What will your guess that how does the matrix look like? You will be saying the matrix might be looking like this. Okay, there are only two options left for the matrix. Either the matrix look like this, just two columns, or it may be possible just one column only. Okay, it may be also possible. Either A is this or A is this, right? So basically, if you say that A is m cross n, m cross n, so that is for sure the number of rows are actually three. Okay, three cross. It could be either two, or it could be either one, but it must be linearly independent, right? So what could be the rank? If the matrix is this, then rank is 2. If the matrix is this, then rank is 1, isn't it? So let's just see the options here actually. So rank can be 2 or rank can be 1. Both are the true. Both are true cases. Okay, because the matrix could be like this, or the matrix could be like this. I mean, this is a vector also, but this is a matrix also. Okay, m equal to 3. M is number of rows. Yes, actually m is 3. Okay, they are saying can be true. So actually m must be true. I mean, this is actually 3 only. But number of columns can it be 1? Yes, there can be 1. They can be 2 also. Okay, they can be 2 also. Number of columns can be 2 also. So basically A, B, C, D are the correct answers. This was a good question. Okay. Number of columns, n means number of columns. Okay, so number of columns can be 2 or it can be 1. So they are saying that can. Okay, so number of columns can be 2. Understood? Okay, so now I hope that is okay to everyone. Let me know if there is any doubt in this question. It was a good question actually. Okay, so whenever you see this, okay, then it actually means that they are saying for some vector you have no solution, for some vector you have exactly one solution. Okay, then you can infer that what they are trying to say, right? So just treat it as a sum vector, not like exactly. Don't go with exact values. If you treat it like, okay, for some vector you have solution, for some vector you don't have solution, then you will be able to answer this question, right? Okay. So instead of can, let's suppose there is a must. Which of the following must be true? Then what is the answer? Can you tell me what is the answer in that case? Which of the following must be true? Yes. So in case of must, okay, number of rows are fixed, which is 3, right? Rank can be 1, can be 2. So it can be 2. It need not to be exactly 2. It can be 1 also. So that is why only B will be the answer. In case of must, only B will be the answer. Okay. Great. Now let's just see this question. Let's see what this question is saying. They are saying 3 cross 3 matrix, 3 by 3 matrix B is known to have eigenvalue 0, 1, 2. This information is enough to find which of the following. Give the answers. Okay, which of these this information is able to find. I mean, you can find out which of these following value with this information. So they are saying the eigenvalues are 0, 1, 2. Okay, three distinct eigenvalues you have. Now can you tell me, corresponding to 0, how many linearly independent eigenvectors will be there? See, exactly one corresponding to each, right? Are you getting my point? Basically, linearly independent eigenvectors, if you are having 0 twice, then maybe 1, okay, or maybe 2. Or if you are repeating, if you are having the repeating eigenvalues, then in that case you will be confused. Maybe linearly independent eigenvectors maybe 1 or maybe 2. Okay, because at most 2, or maybe if these are repeating 3 times, then at most 3 linearly independent. But here exactly one linearly independent, exactly one linearly independent, like this, right? So basically, what I'm trying to say, that nullity is actually one only. Okay, I mean here, if it is not repeating more than one, the nullity is actually one. Okay, nullity is one. So which means rank you can find out, which is 3 minus 1, which is 2, because 3 is number of eigenvalues or number of columns. Okay, 3 cross 3 matrix. So basically, rank you can find out. Rank you can find out. There is no problem in rank. So they are saying which of the following you can find out. Rank you can find out. What about determinant? See, determinant of B. Can you tell me determinant of B? If the one of the eigenvalue is 0, then if you multiply these eigenvalues, then determinant will be 0 only. Then what about determinant of B transpose B? It will be determinant of B transpose into determinant of B, which is just 0 only. Okay. So determinant also you can find out. What about the eigenvalues of B square plus I power minus 1 or inverse? So the eigenvalues of this will be like this: 1 upon lambda square plus 1. Okay. So the first eigenvalue will be 1 upon 0 plus 1, which is 1, 1 upon 1 plus 1, and 1 upon 4 plus 1, right? Like this. So these are the eigenvalues of B square plus I inverse. So basically, you can find out the eigenvalues of this also. But what about the eigenvalues of B transpose B? So there is no way to find out the eigenvalues of B transpose B. So you can find out the eigenvalues of the polynomial. Okay. So polynomial of B. You might remember from Kelly-Hamilton theorem, right? So basically, eigenvalues of polynomial of B is very easy to find out. Okay. If it is B square or anything like this, then it is lambda square plus, instead of I you will be having 1, lambda square plus 1. Inverse means 1 upon lambda square plus 1. These are the eigenvalues of B square plus I inverse. But the eigenvalues of B transpose B, there is no way to find out using the eigenvalues of B. Okay. So C you cannot find out, but yes, A, B, D are the correct answers here. So let's just check it. So for the C, not enough information to conclude the eigenvalues, right? And otherwise for the D, as I told you, these are the eigenvalues, right? Okay. So rank you can find out. Rank will be actually 2. Determinant you can find out, which is 0. Okay. And eigenvalues of these are like this. So here, C is not the correct answer, but A, B, D are the correct answers. Okay, great. Now let's just move to the next question. So in this question, they are saying that let A be the matrix which is M cross N matrix. Okay, A be a M cross N matrix. Consider the system of linear equations AX equal to B, which of the following is always true. Okay, so they are saying suppose M is greater than N, then rank of augmented matrix A given B cannot be larger than M. M is number of rows. Okay, so these are the number of rows. Let's suppose these are the 3 rows and 2 columns. So tell me, can if you just add one more column, see, let's suppose, let me have 4 rows. If you have one more column, can it be 5? Can the rank be 5? No, right? So cannot be larger than M. So basically, this is true. Is this fine to everyone? Let me know. So they are saying true, right? So A is the correct answer, but let's just see other options also. Suppose A is full rank, then AX equal to B always have solution. Okay. So AX equal to B always have solution. So basically, it means that it full rank means it actually means full column rank. Okay, which means all the columns are linearly independent. Okay, full rank generally means that full. I think full rank means the full. They're talking about the column. So if all the columns are linearly independent, then does this mean it always have the solution? No, right? So that is why this is false. I mean, just saying that okay, columns are linearly independent does not mean you always have the solution. AX equal to B has a solution, then AX equal to 0 has unique solution. If AX equal to B has a solution, okay, in that case, See, they are not talking about unique or any number of solutions here. So if ax equal to b has a solution, which means you can say that so solutions could be infinite solution on uh, could be just unique solution also. So they're not talking about this, right? Whether it is infinite or unique solution. So ax equal to b, if we have unique solution, then it means linearly independent. Then in that case, ax equal to 0 also has unique solution. If ax equal to b, see, if I say if ax equal to b has unique solution, then ax equal to 0 has unique solution. Is this true or not? Tell me. Is this true? This particular line, whatever I have written on this screen. This is true, right? If ax equal to b has unique solution, what does this mean? It means columns are linearly independent. Then ax equal to 0 also has unique solution. But if I just say ax equal to b has solution, okay, then columns may be linearly dependent or may be linearly independent. Then you don't know whether it has unique solution or infinite solution. So that is why this is false. Okay, has a solution cannot claim whether it is unique solution. If ax equal to b has a unique solution, then a has to be invertible. See, for that it has to be square, right? It need not to be even square at the first place. That is why it is false. Okay, need not to be square. So basically only A is true here. Other options are false. Okay, only is true. Great. So yeah, only is true. So let's just move to the next question now. Let's see this question. This question got many upvotes. Okay. If you like any question, just do a simple upvote. Okay. It's very easy to do upvote. So you can just simply do upvote here if you like any question. Now let's just see what this question is saying. They are saying that A is a 3 cross 3 matrix. Suppose A has two eigenvalues, 2 and -1. And suppose U and V are the eigenvectors corresponding to 2 and -1, which means they are saying A U equal to 2U and A V equal to -V. Okay. I mean, these are the eigenvalues and eigenvectors pair. And U and V are also given. Now they are asking A power 5W will be what? See, for this question, first you have to observe what is the relationship between W and U and V. Can you represent W as a linear combination of U and V? Okay. See, if you want 2 here, then probably you have to do 2. Like, I mean, you cannot get 2 from here. So it has to be 2V and 3U, right? 3U plus 2V. It has to be 3U plus 2V. 3 means -3. Yes, it is 3U plus 2V. So W is 3U plus 2V, right? Now, they're asking A power 5W. So instead of finding A power 5W, can you tell me what is A into W? It will be, A into 3U plus 2V. So which is 3AU plus 2AV. And AU is already 2U. So basically it is 3 into 2U plus 2 into -V. So basically it is 6U plus or -2V, right? 6U minus 2V. Now, this is what you got A into W. Okay. Now, if you just multiply A one more time, basically this is the eigenvector, right? So you will be getting. I mean, you will be basically, or instead of doing like this, let me just tell you that if you have AU equal to 2U, can you tell me what is the A power 5 U equal to? It will be just 2 power 5U. Okay, you can just try it out. How? You just multiply by A both sides. It will be A square U will be 2 into AU, and AU just 2U, right? So 2 square U like that, right? So basically A power 5U equal to 2 power 5U. Similarly, a power 5 v is equal to minus 1 power 5v, right? Minus 1 power 5v, or in other words, it is just minus v. Okay, so these are the two equations we have. Now one more thing we know, that w equal to 3u plus 2v, and now they're asking a power 5w, so which means they're asking 3 into a power 5u plus 2 into a power 5v, right? So a power 5u is nothing but 2 power 5u. Okay, so 3 into 2 power 5u plus 2 into minus 1 power 5v. That's what they're asking. If you just substitute the value of u and v, which is actually given, you will be getting your answer. Okay, so this is the answer. You just need to substitute the value of u and v. So if you do this, then this will be the answer. Understood? Okay. So it was just a little observational question, that how to solve this question, because in GATE also they ask sometimes these kind of questions. So you just need to observe that, okay, how to do this question. So just see that, okay, W is a linear combination of this, and then you just need to observe that, okay, this is also the possible equations. Actually, these are actually popular equations, which is not in our syllabus, but yes, in general, these are actually very, very popular equations. And also we can also infer that if I just ask you what is the eigenvalue of a power k, if I ask you the eigenvalue of polynomial, then you know that it will be just lambda power k, right? So if ax equal to lambda x is there, then a power k x equal to will be lambda power kx, because lambda power k is the eigenvalue of a power k. Okay, so you can understand like that also, or maybe you can understand like this also. So let me know if you have understood this. So basically, you just need to observe that W is a linear combination of this, and then you need to proceed with this question. Okay. So it was a good question. Don't worry if you were not able to solve this in an exam, or maybe if you have seen this later on. If you are not able to solve, that is fine. But now you understood that, okay, for these kind of power question, the only possibility is that W should be the linear combination of eigenvectors. Because for the eigenvectors, we directly know the powers. How to handle the powers with the eigenvector, you directly know, right? So here W should be the linear combination of the eigenvectors. That is the only possibility left. Because for the eigenvectors, okay, for the eigenvectors, if V is an eigenvector, then I can directly say the power is like this. Okay. For the eigenvectors, the power is very easy. Okay. Now let's solve this question. This question was actually interesting question. This question was related to one, theorem. Do you remember one theorem, that AB and BA have same? Can you just complete this statement? This was, told in one of the lecture. Can you just complete this statement? Have same non-zero eigenvalues. Do you remember this? Okay. So I hope you remember. So AB and BA have same non-zero eigenvalues. So basically, if you just consider this a matrix, okay, although it is a vector, but vector is also a matrix, right? If you just consider this a matrix, and if you also consider this a matrix, so suppose these are the two matrices, right? This and this. So this is like some matrix, okay, which is basically, if you just multiply these two matrices, you are getting one, okay, just one. So the eigenvalues of AB, okay, the multiplication of these two matrices, just one only, because the matrix itself is one. So just tell me the eigenvalues of this. Just tell me the eigenvalue of this matrix. It is one only, right? Eigenvalue of this matrix is just one. So basically you can treat this one as a constant or this one as a matrix, doesn't matter. So the eigenvalue of this U transpose U, the eigenvalue of U transpose of U is just one, right? Do you all agree with me on this? So I can say eigenvalues, right? If AB, okay, has this eigenvalue, then if I just ask you the eigenvalue of UU transpose, okay, UU transpose, some other matrix, If I just flip it, if I just ask you the eigenvalues of this, since it is just having only one non-zero eigenvalue, then can you tell me what are the non-zero eigenvalues here? Just one, right? Just one. So non-zero eigenvalues will be just one, right? So here, if I just ask you non-zero eigenvalues, just one only. Okay. And other eigenvalues could be 0, 0 or something like this. But if this 0, 0 doesn't contribute in the summation, see, they are asking a sum. Okay. So if the other eigenvalues are 0, 0, it cannot be non-zero actually. So non-zero eigenvalue is just one. And if you sum all the eigenvalues, then the summation will be one. Okay, the summation will be one. So one is the correct answer here. Actually, a similar kind of question has already been asked in GATE. I just flipped this question, and I can say similar kind of question was actually asked in one of the interview in IIT. Okay, one of the IIT professor has asked this question to Go classes student. His name was Abhishek Solanki. I think in GATE 2023. Okay, he's ISC pass out recently. He graduated from ISC. In GATE 2023, this question was asked to Abhishek Solanki. His rank was 149, AIR 149. Okay, and he actually shared this question with me. And at that moment, I decided to put this question in the weekly quiz or in the test series or in, I mean, in Go classes curriculum. Okay, somewhere either in weekly quiz or test series like that. So I hope you understood this question. Let me know if there is any doubt in this question. So basically, the eigenvalues, the one thing you have to notice that eigenvalues of AB and BA, the non-zero eigenvalues should be same. So eigenvalues of U transpose U is 1. So non-zero eigenvalues of U transpose will be 1. Other eigenvalues will be 0. Okay. Is this clear to everyone? So the summation will be 1 only. Let me know. Okay, great. Now let's just move to the next question. Okay. So one will be the non-zero eigenvalue. Other eigenvalues could be there, but those will be zeros. So summation will be 1 only. Now let's just see this question. Okay. What they're asking. They're saying consider these below statements. Okay. First statement M is less than N. Second statement A has M linearly independent columns. Third statement, there is a solution uh, for every B in R power M. So let's just see which of the following are always true. S gives R. See, if M is less than N, does this convey anything? Tell me. Does this convey anything? That you have a solution or not if M is less than N? So actually, I can say that this A and C will be false. I mean, M is less than N will not convey anything. Okay, whether you have solution for every V, you whether M linearly independent columns or like that, right? So A and C are clearly false. Let's just check whether this B or D are true or not. B is saying R gives P. R means there is a solution for every B. Okay, so if you have solution which means you are filling the space, then A has M linearly independent columns. Yes, so basically if you are filling the space in Rn, okay, so A is M cross N, which means M rows. Okay, so this is an Rm, right? Now there is a solution for every B. If you have solution for every B, it means you are filling the space. So A must be basically having M linearly independent columns. So that is why B is true. Is this fine to everyone? Let me know. Is this fine? Right? Now let's just check this option D also. So D is saying that S and P. S means this and P means this. A has M linearly independent columns. Okay. So let's suppose this is 2 cross 3, right? Two linearly independent columns. Let's suppose A has. Sorry. Uh, yes, M is less than N. So 2 cross 3. And P. P means two linearly independent columns. So 2 rows and 3 columns, right? So A has two linearly independent columns. Let's suppose you are filling the space of R2. Okay. In that case, there is a solution in R2. What do you think? So if you're filling the space of R2, two linearly dependent columns you have in R2. Now they're asking whether you have a solution for every B in R2. This is true, right? This is true. So if you have two linearly independent columns in R2, right? So if you have two linearly independent columns in R2, and then you are saying that okay, you have solution for every B in R2, that is true. That is actually true. So B and D are the correct answers here. Understood? Let me know if there is any doubt in this particular question. Okay. So now let's just see this question. What this question is saying. Consider the following set of column vectors. Okay. So basically this is some column vector. I mean, this is a set of column vectors and they are following these rules. Now, which of the following are true? Every element of the set X can be written as linear combination of S. This something like this. Okay. So let's just do one thing. Let me just take these two vectors on the next page. Okay. So let's just see that what is the relation of this particular set and these vectors. I mean, how these two vectors might be related to this particular set. So see, isn't it a system of linear equation? I mean, that is only one equation which I agree, but isn't it a system of linear equation? Something like this. I mean, something like this, right? Do you agree with me that if you want to write this in matrix format, then you will be writing something like this? Let me know. Do you all agree with me on this? Okay. Now, uh, now let's just do one thing. Let's just solve the system of linear equations. Okay. So let's just assume how to solve. First, we will be basically making a pivot, and then we will be having the free variables, and then we will be assuming, let's suppose x3 equal to k1 or k2, something like this, right? X2 equal to k1, something like this, right? So what will be the x1? So it is 2x1 will be equal to minus 3k1 plus k2, something like this, right? So x1 will be minus 3 minus 3y2 k1 plus 1 by 2 k2. Is this fine to everyone? Okay. So basically, you can say the system of linear equation has this solution, which is like k1, k2, okay, and then there will be minus 3 by 2 k1. Let me make some space here. Minus 3 by 2 k1 plus 1 by 2 k2. Okay. Now, I hope that is understood to everyone. Now, let me go to the next page. Now, let's just write this particular, you know, vector. So basically, you can say that here, the vectors here will look like this only, isn't it? The vectors here will look like this. Or if you take, if you want, you can take x1 as k1, k2. So basically, you can also have something like this. See, I mean, that is up to you, which you are making k1 and k2. But if you have x1 as k1 and k2, then if x1 you can take k1, x2 if you take k2, then the vectors will look like this. K1, x1 is k1, x2 is k2. In that case, x3 will be 2k1 plus 3k2. Okay. So the vectors here will look like this. I mean, basically the vectors should satisfy, these three numbers should satisfy this. Okay. So either you write like this or you write like this, doesn't matter. But yeah, these three numbers should be basically making, I mean, if you're taking these two as free, then this is basically pivot. Okay. I hope that is fine to everyone. Now you can just decompose this further. It will be equal to K1 into something and K2 into something. Okay. Can you decompose and let me know what will be the answer? So it is 1. So you can just write 1 in place of K1, 0 here, 2 here, right? So 1, 0, 2. You can write in place of K2, you can write 1. K1 will be 0. I mean, everything will be 0, but just K2 will be 1, 3, right? So 103, 102. Is this fine to everyone? Sorry, 013 and 102. Is this fine? Let me know. Okay. So maybe you can see from here something you can are you able to see something? Let me know. So by the way, till this point it is fine, and then we will be proceeding further. So basically, the thing here is that all the vectors here in this particular set, okay, all the vectors here in this particular set will look like this, right? Will look like this. I mean, they will be the linear combination of these two columns, right? So all the vectors here will be the linear combination of these two columns. Now, in the question, they are saying all the vectors here are the linear combination of these two columns. See, this column is same, but this column is nothing but this one only. I mean, if you just uh, if you just subtract this minus this, okay, then you will be getting this. See, if you just subtract this minus this, then you will be getting this. So basically this column, you can say this column is nothing but, in other words, uh, let me write like this. This will be basically 102 minus 013. I mean, this column is nothing. I mean, this column is actually having it is having this column already inside it. Okay. I mean, this column already having this column inside it. So basically, these two columns are nothing but these two columns only. See, this column you are able to see directly. Okay. This column you are able to see directly. What about this column? So this column already has, inside this column, you already have this. You extra have this, which is okay. I mean, which is okay because you already have this, and whatever you see, I don't want to make it complicated, but whatever effect this is creating, it can be, by choosing the correct coefficient, you can basically nullify this. Okay. So what I'm trying to say, that these two columns and these two columns as a linear combination, if I say, then these two columns and these two columns are actually same. If I'm saying that all the columns are linear combination of these two, then it is same as saying that all the columns are linear combination of these two also. So basically here these two are, if you are saying that all the columns will be the linear combination of these two, then this is true. And is this a linearly independent set? See, first tell me, is this a linearly independent set? Yes, right. I mean, if you just look at these two, then you will be saying that okay, this is a linearly independent set, isn't it? So yes, this is a linearly independent set. Now, are these two linearly independent? Obviously, I mean, this already has something which is linearly independent of this, right? So yes, these two are also linearly independent. So basically, both the statements here are true. Okay. So see, for this particular question, you just need to see that what are the linear combination of the columns that this particular set is having. And how to see this? You can just make any two, which are actually any two as free variables. I have made first two. The reason is that because if I make third as a pivot, then I don't have to do y2 or something. So basically, x3 can directly be 2x1 plus 3x2. So in other words, you can write like this. I mean, all the columns will be like this. X1, x2 you can choose by your own, but x3 will be 2x1 plus 3x2. Okay. X3 will be like this. So yes, this was a good question. So both the statements are true here. Okay. Now let's just see this question. This question was also good, or you can say interesting question. They are saying that for which value b. Oh, they're asking about by the way the correct statements. So they are saying for which value b. This is invertible. For the invertible matrix, that's very easy. You just can find out the determinant of this. This is 2 by 2, right? So this is basically 2 minus 3b. It should not be 0. So if b is not equal to 2 by 3, right? Then it is invertible. Then what about option A? Option A is saying if b is greater than this, then it is invertible. Is this true or false? This is interesting. See, just tell me, okay, if b is greater than 2 by 3, then obviously invertible, right? For other values also invertible. If b is less than 2 by 3, then also invertible. But they're not talking about this. They're just saying if b is greater than 2 by 3, then invertible. Yes, that is true actually. That is true. If b is less than 2 by 3, then invertible. Is this also true? Yes, this is also true. This is also true. If b is equal to 5, then invertible. This is also true. This is also true. Okay. All these are true. Understood? Okay. So this is true. What the next statement is saying. If P is invertible matrix such that B equal to P inverse AP, then determinant. Okay. If you find out the determinant, then it will be 1 by P into determinant of A into P, right? So yes, P and 1 by P will get cancelled out. So okay, I don't have the solution. See. So determinant of B is equal to determinant of P, 1 upon determinant of P, determinant of A, right? So actually, this will get cancelled out. So it is the determinant of A only. So determinant of A and determinant of B are same. So this is true. This is also true. What about this? They are saying let me write this here. So in option C, they are saying let A be the matrix which is M cross N and A is actually P inverse. Okay, something like this. Where a P is invertible and D is a diagonal matrix. Then can you find the power of A? Okay, they're just interested in finding the power of A. So what is A square? It is nothing but A into A, which is nothing but P inverse into P inverse. Now, interestingly, this P inverse P will get cancelled out. So that is why it is P into D square. D square means that this is diagonal matrix and then you can take a square of this, which means that each element is square. So basically, whatever these elements are, you can directly put a square of the elements, okay, for the diagonal matrix. Okay, D square. So this is okay. This D square is okay. And then P inverse, okay. P inverse is only left. So A square is P D square P inverse. Similarly, what is A power K? It will be D power K P inverse, right? I mean, if you keep on multiplying, and you can just, whatever power you are putting here, you can directly put the power here. Okay. So we will see for the gate DA students, we will see this in the similar matricized diagonalization. For these kind of topics, we will see more applications of this. Okay, later on. For the gate DA students. Yeah, for gate CS students, we will not see applications of this, but for gate DA students, we will see. Okay. So yes, C is also true. What about D? If you have M equal to N, then always have solution. No, that is false, right? I mean, why will we always be having the solution? Okay. I hope that is understood to everyone. So, I mean, there is no reason to have always have solution. So that is why this is false. Okay. So let me know if that is understood. Okay. So someone is asking, it's linearly independent, then it will be having the solution. Yes. In case the columns are linearly independent, yes. Then in that case, it will always be having the solution. Yes, that is true. Okay. If the columns are linearly independent, then if M equal to N and columns are linearly independent, then yes, always have the solution. Okay, that's a nice observation. If M equal to N and columns are linearly independent, then always have the solution. That is true. Okay. So now let's just see this particular question. What this question is saying. If B is linearly dependent on columns of matrix, okay, then it need not be always a unique solution. If B is linearly dependent on columns, yes, that is true, right? I mean, it need not to be unique solution basically. If columns of matrix are linearly dependent, then above system of equation can have a unique solution. Is this true? No, this is false. So this is clearly false, right? So this is false. So I can say S1 is true, but S2 is false. Okay. Yes. So we have seen this multiple times, right? That if columns are linearly dependent, then unique solution cannot be there. We have seen this multiple times. Okay. So let's see this. So in this question, this is actually interesting question. This is symmetric matrix. In the symmetric matrix, they are saying that okay, this is, if this is 1, 2, 3, and this is 2, 4, 6. What do you observe? The 1, 2, 3 is basically the eigenvector with the eigenvalue 2. I mean, this is 2 into 1, 2, 3 only, right? So this 1, 2, 3 is eigenvector. Similarly, this is also the eigenvector with the eigenvalue -1. I mean, these two are actually eigenvectors. Okay. But is this possible? See, they are saying, um, let's suppose this is V1. Okay. The eigenvalue is 2. Okay. Let's suppose this is V2. The eigenvalue is -1. They are saying something like this. Okay. I mean, V1, V2 has to be the eigenvector. I mean, that is given here. Okay. By just observation, you can check that, okay, that is true, right? Now, is this possible for the symmetric matrix? See, the eigenvalues are 2 and -1, right? For the distinct eigenvalues in the symmetric matrix, the eigenvectors have to be orthogonal actually. Okay, so this and this have to be orthogonal. Are these orthogonal? See, let me just tell you one of the property of the symmetric matrices. Do you remember the properties of symmetric matrices? See, this is one very nice answer written by Suraj Reddy. Do you know Suraj Reddy? Anyone knows like what was his rank in GATE 2024? I think it was 51, right? AR 51 or 52. I think 51. AR 51 in GATE 2024. Okay, in GATE CSE. He is one of the topper. He has written very nice answer. So anyway, I just wanted to focus on these two properties. That if it is symmetric matrix, real symmetric matrix, then eigenvectors of distinct eigenvalues are orthogonal. So they have to be orthogonal. So B1 and B2 have to be orthogonal for this to be true. So is this possible to have these eigenvectors? No, right? Because 1, 2, 3 and 2, 1, 0. If you just multiply, there is 2, this is 2, 2 plus 0. I mean, this is 2, and this is 0, right? So 2 plus 0 is not 0. Okay. 2 plus 0 is actually 4, not 0. So these are not orthogonal. Since these are not orthogonal, that is why you will say it is not even possible to have something like this. If S is symmetric matrix, then statement 1 is not even possible. Understood? Or no? Let me know. Not even possible. Because V1 and V2, which are eigenvectors, which are supposedly eigenvectors basically, are not orthogonal. Okay. This is not even possible. Is this statement too possible? See, if you take the determinant both sides, okay, then what is the determinant of S square? It will be determinant of S into determinant of S, which will be some positive number. Okay, which will be some positive number. See, determinant of S square will be determinant of S into determinant of S, which will be some positive number. And what is the determinant? See, I here is 3 cross 3 basically. Okay, so if you notice 3 cross 3. Tell me what is the determinant of S square? It will be determinant of S into determinant of S. What is the determinant of minus I? It will be -1 power. Determinant -1 power how much? If this is 3 cross 3, tell me. It will be 3. Do you remember? So it will be -1 into 1, which is -1. So basically here the determinant is -1. Okay, here the determinant is -1. But here the determinant must be positive. See, determinant of this S will be some it could be positive or negative, but yeah, ultimately multiplying two numbers will be positive number only, right? So it is a positive number. It is a negative number. So that is why it is not possible to have these two matrices same. Because determinant of this will be positive, determinant of this will be negative. How they can be same? Right? So that is why this is also not possible. Okay. So both statements are false. Both statements are false. This is a good question. Again, this question is also little observational, that you need to observe that, okay, these are the eigenvectors, you need to take the determinant and all. But these are just practice questions. Just take them as a practice question so that you are better ready for gate. Let me know if that is understood. Okay, clear, right? So that is all I wanted to discuss in this session, right? Great. So there are many questions we have discussed. I hope you understood most of them. Uh, So this same question, similar question, I think have been asked in CMI. So you can just check that question. I don't have that question as of now, but yeah, a similar question has been asked in CMI also. CMI means Chennai Mathematical Institute. Okay. So thank you, everyone.